Let us first study the properties of phosphine. Phosphine is a colorless and extremely poisonous gas that smells like garlic or rotten fish. Unlike ammonia, it is slightly soluble in water, and the aqueous solution is neutral. It is more soluble in carbon disulfide and other organic solvents. The melting and boiling points of phosphine are much less than that of ammonia due to the absence of hydrogen bonding. It condenses to a colorless liquid at -87 degrees Celsius and freezes at -132 degrees Celsius. Phosphine acts as a Lewis base analogous to ammonia due to the presence of a lone pair of electrons. However, it is a weaker base than ammonia because its central atom, phosphorus, is larger in size and less electronegative. Its basic character is evident from its reactivity towards anhydrous halogen acids such as anhydrous hydrogen iodide. Phosphine combines with hydrogen iodide, thereby acting as a Lewis base by donating its lone pair to form phosphonium iodide salt. Talking about phosphonium salts, the phosphonium ion has a structure similar to the ammonium ion as shown here. Do you know why the bond angle of phosphonium ion is higher than that of phosphine? Try to answer this question on your own before looking at the answer. The central phosphorus atom is tetravalent in phosphonium ion and trivalent in phosphine. This indicates that there are 1 lone pair and 3 bond pairs in phosphine. While all the 4 are bond pairs in phosphonium ion, you know that the magnitude of repulsion between a lone pair and a bond pair is greater than between 2 bond pairs. Hence, the extent of repulsive interaction in phosphonium is less than in phosphine. As a result, the bond angle in phosphonium ion is greater than in phosphine. Pure phosphine is non-combustible at normal conditions, but catches fire when heated to about 150 degrees Celsius to form phosphoric acid. When phosphine is heated to about 440 degrees Celsius in an inert atmosphere, or when it is subjected to an electric spark, it decomposes into its constituents, namely red phosphorus and hydrogen. Also, an aqueous solution of phosphine decomposes in the presence of light into red phosphorus and hydrogen. It burns with an explosion when it comes in contact with even the smallest amounts of oxidizing agents such as nitric acid and chlorine gas. Nitric acid oxidizes phosphine to phosphorus pentoxide and itself gets reduced to nitrogen dioxide as shown in the equation here. Similarly, the equation corresponding to the oxidation of phosphine in the presence of chlorine is also shown. When passed through aqueous metallic salt solutions such as copper sulfate, silver nitrate, and mercuric chloride, phosphine gas precipitates the corresponding metal phosphides. As can be seen from these equations, copper phosphide is precipitated from copper sulfate, silver phosphide from silver nitrate, and mercuric phosphide from mercuric chloride. You know that the reducing power of the hydrides of group 15 elements gradually increases on descending the group. Hence, the reducing power of phosphine is greater than its analogue ammonia. It reduces auric chloride to metallic gold, as shown in the equation here. Let us now turn to the uses of phosphine. The hydrolysis of calcium phosphide finds use in the manufacture of Holmes signals. A mixture of calcium phosphide and calcium carbide is taken in a container and sealed. When needed, the container is pierced and thrown into the sea. As water enters the container, it reacts with the mixture and produces brilliant flashes of light, a bright luminous flame which serves as a signal to approaching ships. The bright luminous flame is due to the formation of phosphine and acetylene on the hydrolysis of calcium phosphide and calcium carbide. Note that the spontaneous flammability of phosphine is due to the presence of diphosphine. The same reaction is also used in smoke screens. The phosphine obtained catches fire and produces the required smoke. You know that phosphorus forms two types of halides, namely px3 and px5. Here, X represents a halogen, which may be fluorine, chlorine, bromine, or iodine. Of these, chlorides are more common. These chlorides are covalent in nature. Let's first study the preparation and properties of phosphorus trichloride. In the laboratory, phosphorus trichloride is prepared by heating white phosphorus in a current of dry chlorine. Let's take a quick look at the method of preparation. The apparatus required is arranged as shown here. White phosphorus is placed in a retort and gently heated over a water bath. A current of pure and dry chlorine gas is passed over the white phosphorus. Phosphorus trichloride distills off, and the vapors are condensed in a water-cooled receiver. Phosphorus trichloride can also be prepared by the action of white phosphorus on thionyl chloride. The equation for this reaction is given here. Talking about its structure, the central phosphorus atom in phosphorus trichloride undergoes sp3 hybridization with 3 bond pairs and 1 lone pair of electrons. On account of this, it has a pyramidal shape. It acts as a Lewis base due to its ability to donate its lone pair of electrons to other electron-deficient ions or molecules. Let us now turn to the properties of phosphorus trichloride. It is a colorless liquid with a pungent smell. It has a very low boiling point of 74 degrees Celsius. It reacts violently with water and gets hydrolyzed to form phosphorus acid and fumes of hydrochloric acid. As a consequence, it fumes in moist air. Similarly, it reacts with organic compounds that contain hydroxyl groups such as acetic acid and ethyl alcohol to form phosphorus acid as the main product. Let's now move on to the preparation and properties of phosphorus pentachloride. In the laboratory, phosphorus pentachloride is generally prepared by passing excess chlorine into a solution of phosphorus trichloride in carbon tetrachloride. Phosphorus pentachloride can also be prepared by using these methods. Let us now discuss the properties of phosphorus pentachloride. Phosphorus pentachloride is a yellowish-white crystalline powder. It sublimes on heating at 160 degrees Celsius. On strong heating, phosphorus pentachloride dissociates into phosphorus trichloride and chlorine as shown in the equation here. Phosphorus pentachloride reacts violently with excess of water to form phosphoric acid. In other words, phosphorus pentachloride, on complete hydrolysis, gives phosphoric acid. Note that it forms phosphoryl chloride or phosphorus oxochloride and hydrochloric acid when equimolar amounts of phosphorus pentachloride and water are used. In other words, when water is taken in small amounts, the products formed are phosphorus oxochloride and hydrochloric acid. Now, write a balanced chemical equation for the hydrolytic reaction of phosphorus pentachloride with heavy water. Try this on your own before looking at the answer. Here are the balanced chemical equations for the reactions of phosphorus pentachloride with small amounts of D2O and excess of D2O. Just like phosphorus trichloride, phosphorus pentachloride also reacts with organic compounds that contain hydroxyl groups. It replaces the hydroxyl groups in the compounds with chlorine atoms. For example, the hydroxyl groups in ethyl alcohol and acetic acid are replaced by chlorine atoms to form chloroderivatives, namely ethyl chloride and acetyl chloride, as shown here. When heated with finely divided metals such as copper, silver, and tin, Phosphorus Pentachloride forms the corresponding chlorides, namely cuprous chloride, argentous chloride, and stannic chloride. Next, let us look more closely at the structure of Phosphorus Pentachloride. The central phosphorus atom in Phosphorus Pentachloride undergoes sp3d hybridization. From the VSEPR theory, you know that since all the 5 electron pairs in these hybrid orbitals are bond pairs, the geometry of the molecule is trigonal pyramidal, as shown here. Of the 5 hybrid orbitals, 3 occupy equatorial positions, while the remaining 2 occupy axial positions. As a consequence, 2 different bond angles are observed in the molecule. They are 120 degrees and 90 degrees. Also note that the 3 equatorial PCl bonds are equivalent with bond lengths of 202 picometers, while the 2 axial PCl bonds are longer than equatorial bonds with bond lengths of 240 picometers. Trigonal bipyramidal geometry is observed only in its liquid and gaseous states. However, in the solid state, it exists as a salt, that is, as an ionic solid in which the cation tetrachlorophosphonium is tetrahedral, while the anion hexachlorophosphate 5 is octahedral, as shown here. Phosphorus forms a number of oxoacids, such as hypophosphorus acid, orthophosphoric acid, pyrophosphoric acid, hypophosphoric acid, orthophosphoric acid, pyrophosphoric acid, and metaphosphoric acid. The table here lists the formula and oxidation state of each of these oxoacids. Phosphorus usually exhibits an oxidation state of either +3 or +5 in its oxoacids. Note that the oxidation state of phosphorus in hyperphosphorus acid is +1, while it is +4 in hyperphosphoric acid. The oxoacids in which phosphorus exhibits lower oxidation state of +1 or +3 constitute the phosphorus acid series, while the ones in which phosphorus exhibits higher oxidation states of +4 or +5 constitute the phosphoric acid series. Let us first look at some methods to prepare oxoacids belonging to the phosphorus acid series. Hyperphosphorus acid, also called phosphinic acid, is prepared by the alkaline hydrolysis of white phosphorus. When white phosphorus is heated with an alkali solution, like barium hydroxide, it forms hypophosphite. This is further treated with dilute sulfuric acid to recover the acid. The hydrolysis of phosphorus trioxide or phosphorus trichloride forms orthophosphorus acid, phosphonic acid, or simply phosphorus acid. Orthophosphorus acid can be conveniently prepared by passing chlorine gas through water containing molten white phosphorus. The phosphorus trichloride so formed is instantly hydrolyzed to give orthophosphorus acid. Orthophosphorus acid, when treated with phosphorus trichloride, gives pyrophosphorus acid. Let us now discuss some methods to prepare oxoacids belonging to the phosphoric acid series. Hyperphosphoric acid is obtained by the alkaline hydrolysis and oxidation of red phosphorus. As shown by these set of equations. Orthophosphoric acid, also called phosphoric acid, is industrially the most important oxoacid of phosphorus. It is prepared by dissolving phosphorus pentoxide in water and then boiling the solution. The stepwise process of the hydrolysis of phosphorus pentoxide is represented here. When phosphoric acid is heated gently to about 220 degrees Celsius, it loses water molecules to form pyrophosphoric acid. Pyrophosphoric acid or orthophosphoric acid, when heated to red hot, forms metaphosphoric acid. Crystalline phosphorus acid, on being heated with bromine in a sealed tube, gives metaphosphoric acid. Note that metaphosphoric acid exists as a polymer. Cyclotrimetaphosphoric acid and polymetaphosphoric acid are some polymeric forms of metaphosphoric acid. know that phosphorus forms a number of oxoacids, such as hyperphosphorus acid, orthophosphoric acid, pyrophosphorus acid, hyperphosphoric acid, orthophosphoric acid, pyrophosphoric acid, and metaphosphoric acid. Examine the structures of the oxoacids given here. Now, try to list the characteristic bonds and the number of these bonds present in each of these oxoacids before you take a look at the table that has the relevant data. The table here lists the characteristic bonds and the number of these bonds in each of these oxoacids. Let us now discuss the common and some important features of the structures of the oxoacids of phosphorus. In all of these oxoacids, the central phosphorus atom is surrounded tetrahedrally by other atoms. At least one P double bond O and one POH bond are essentially present in all of these oxoacids. Note that the double bond is formed as a result of the P-pi back bonding. However, pH bonds are present only in the oxoacids belonging to the phosphorus acid series. Note that in hyperphosphoric acid, an unusual PP bond is present. Only the hydrogen atoms that are attached to oxygen in POH bonds are ionizable. And impart acidic character to the compound. Thus, the number of ionizable hydrogens determines the basicity of an acid. On the other hand, the pH bond is not ionizable. The pH bonds found in the oxoacids of the phosphorus acid series have reducing properties. In other words, the hydrogen atoms attached directly to the phosphorus atom are not ionizable and confer reducing properties to the compound. Examine the structures of hyperphosphorous acid and orthophosphoric acid. Of these, which oxoacid can reduce silver nitrate to metallic silver? Also justify your answer. Try to answer this question on your own before looking at the answer. It is apparent from the two structures that hyperphosphorous acid contains two pH bonds. Why? There is no pH bond in orthophosphoric acid. Hence, hyperphosphorous acid reduces silver nitrate to metallic silver, as shown by the equation here. Similarly, orthophosphorous acid and pyrophosphorous acid, which belong to the phosphorus acid series, are good reducing agents. Orthophosphoric acid is a tribasic acid. Can you justify this statement before looking at the answer? You know that only the hydrogen atoms that are attached to oxygen in POH bonds are ionizable and impart acidic nature to the compound. From the structure of orthophosphoric acid, it is evident that it has 3 ionizable hydrogen atoms. Hence, it is a tribasic acid. Note the basicity of the remaining oxoacids based on the number of ionizable hydrogens that are listed in the table here. The oxoacids in lower oxidation states of phosphorus +1 and +3 tend to disproportionate to higher and lower oxidation states. The lower oxoacids disproportionate because some of the phosphorus atoms attain the relatively stable +5 oxidation state. For example, orthophosphoric acid, which contains phosphorus in the oxidation state +3, on heating, undergoes disproportionation to form phosphine, which contains phosphorus in the oxidation state -3, and orthophosphoric acid, which contains phosphorus in the oxidation state +5. Also, look at the disproportionation of hypophosphorous acid that takes place upon strong heating. The elements oxygen, sulfur, selenium, tellurium and polonium constitute the 16th vertical column or 6 A group elements in the long form of the periodic table. The first 4 elements of the group are collectively called chalcogens or ore-forming elements. Because a large number of metal ores are found in the Earth's crust as oxides or sulfides. Oxygen is the most abundant element available in nature. It forms 20.946% of air by volume and 46.6% of the Earth's mass, mostly in the form of silicates and other compounds like carbonates, sulfates, and oxides. Most of the oxygen in the atmosphere is produced by photosynthesis in plants. It also occurs in the form of ozone, which is an allotrope of oxygen in the upper atmosphere, and protects us from the harmful radiations of the sun. Sulfur is the 16th most abundant element and constitutes about 0.034% by weight of the Earth's crust. In its combined form, sulfur is found in ores in the form of sulfates and sulfides. Sulfates include gypsum, CaSO4, 2H2O, Epsom salt, MgSO4, 7H2O, and barate, BaSO4. Sulfides include zinc blende, ZnS, galena, PbS, and copper pyrites, CuFeS2. Sulfur is also present in organic substances like mustard seeds, eggs, onion, garlic, wool, and hair. Sulfur is available in its free state in the volcanic areas of Sicily, Italy, Japan, America, Russia, and Iceland. Small deposits of sulfur are found in Pakistan and India as well. Natural gas and crude oil are other sources of sulfur. Selenium and tellurium are present in sulfide ores as metal selenites and tellurides. Polonium is a radioactive element with a half-life of 13.8 days and is very rare. It occurs in nature as a decay product of uranium and thorium minerals. Look at the electronic configuration of these elements. All the elements of this group have 6 electrons in their outer shell and have the general electronic configuration of Ns2Np4. Now, let's look at the atomic and physical properties and their trends in these elements. Let's begin with the atomic and ionic radii of these elements. From the given electronic configuration, we observe that due to the addition of a new principal energy level in each element, the atomic and ionic radii increase from oxygen to polonium. As you can see from the table, oxygen has an exceptionally small size. This is due to the higher effective nuclear charge of the oxygen atom. You already know that as we move down a group, ionization enthalpy decreases with an increase in the size of the atom. In group 16 elements too, the ionization enthalpy decreases with an increase in the size of the atom from oxygen to polonium. However, note that the elements of this group have lower values of ionization enthalpy than that of group 15 elements. This is because group 15 elements have a stable half-filled p subshell in their valence shell. Due to the extra stability of their half-filled configuration, more energy is required to remove electrons compared to group 16 elements. Let's now see the electron gain enthalpy of these elements. In general, down a group, electron gain enthalpy decreases with an increase in the size of the atom. Thus, the electron gain enthalpy of group 16 elements decreases with an increase in the size of the atom from oxygen to polonium. However, note that the oxygen atom has a less negative electron gain enthalpy than sulfur. This is because oxygen, due to its compact nature, experiences more repulsion between the electrons already present and the incoming electron. Due to these electron-electron repulsions, an oxygen atom has lesser tendency than a sulfur atom to accept the extra electron. Let's look at the trend in electronegativity. As we move down the group from oxygen to polonium, the electronegativity decreases gradually with an increase in the atomic size. Note that oxygen is the second most electronegative atom after fluorine. Let's now learn about the physical properties of the group 16 elements. Oxygen and sulfur are nonmetals. Selenium and tellurium are metalloids, while polonium is a metal under normal conditions. As polonium is a radioactive element, its radioactive property is considered more important than its normal properties. Moreover, its availability is very less as it is a decay product of uranium and thorium. All the elements of group 16 exhibit allotropy. Oxygen has two allotropes, which are oxygen and ozone. Although sulfur has many allotropic forms, only two of them are stable, which are rhombic and monoclinic. Selenium and tellurium exist in both amorphous and crystalline forms. The melting and boiling points of the elements of group 16 increase from oxygen to tellurium as their atomic size increases. This is because, as their atomic size increases, the van der Waals force of attraction between the atoms increases. However, the large difference between the melting and boiling points of oxygen and sulfur may be explained by the fact that oxygen exists as a diatomic molecule, while sulfur exists as a polyatomic molecule. First, let's take a look at the oxidation states of the elements of group 16. As all the elements of this group have a configuration of Ns2np4 in their valence shell, they may attain noble gas configuration either by gaining 2 electrons, forming M2- ions, or by sharing 2 electrons, thus forming 2 covalent bonds. Hence, these elements show both negative and positive oxidation states. The table here gives details of the different oxidation states shown by these elements. The electronegativity of oxygen is very high, second only to fluorine. Therefore, it exhibits a negative oxidation state of -2 in all its metal oxides. Thus, most metal oxides are ionic and contain oxide ions. In addition to -2 oxidation state, oxygen shows -1 oxidation state in peroxides. Since the electronegativities of the elements decrease as we move down the group, the tendency of these elements to show -2 oxidation state decreases from sulfur to polonium. Since polonium has the least electronegativity, it does not show an oxidation state of -2. Instead, it shows only positive oxidation states. Talking about positive oxidation states, oxygen shows positive oxidation state only in its compounds with fluorine, since fluorine is the only element more electronegative than oxygen. It shows +2 oxidation state in oxygen difluoride and +1 in dioxygen difluoride. Note that oxygen does not have d orbitals, and therefore it cannot expand its valency. Hence, the oxygen atom cannot show an oxidation state higher than +2. The other elements of the group, apart from exhibiting +2 oxidation state, also exhibit +4 and +6 oxidation states due to the availability of d orbitals in their atoms. These elements show +4 oxidation state in their compounds with oxygen and +6 oxidation state with fluorine. Due to the inert pair effect, the stability of +6 oxidation state decreases, while the stability of +4 oxidation state increases down the group. Oxygen, like the other p-block elements present in the second period, differs considerably from the rest of the elements in its group. These differences are due to its small size and high electronegativity, and the absence of d orbitals in the valence shell of the atom. The important differences are atomicity, oxygen is diatomic and gaseous, while the other elements have complex structures and hence exist as solids. Formation of N2- ions. Oxygen, due to its high electronegativity, shows negative oxidation state and does not show any positive oxidation state except in oxygen difluoride and dioxygen difluoride. The other elements show +2, +4 and +6 oxidation states in addition to -2 oxidation state. Polonium does not show minus oxidation state. Maximum covalency. Due to the absence of d orbitals in oxygen, its covalency is limited to 2. But the covalency exceeds 4 in the other elements due to the availability of d orbitals in them. Hydrogen bond formation. Because of its small size and high electronegativity, oxygen forms strong hydrogen bonds, which greatly affects the properties of water and other compounds. However, the other elements in the group have comparatively low electronegativities and, therefore, do not form hydrogen bonds. Now, let's discuss the chemical properties of these elements. The elements of this group react with hydrogen to form hydrides of the type H2E. where E could be oxygen, sulfur, selenium, tellurium, or polonium. The physical states, melting points, boiling points, enthalpy of formation, enthalpy of dissociation, and dissociation constants of these hydrides are given in the table here. Let's look at the physical states of these hydrides. Water is a colorless and odorless liquid, while the hydrides of all the other elements of the group are colorless, poisonous gases with unpleasant odors. The boiling point of the hydrides markedly decreases from water to hydrogen sulfide and then increases. Water has an abnormally high boiling point because its molecules are associated with each other by means of hydrogen bonds in its solid as well as liquid states. On moving down the group, the boiling point increases from hydrogen sulfide to hydrogen telluride because of the increase in molecular weight. The thermal stability of these hydrides decreases with a decrease in the bond dissociation enthalpy of the He bond from H2O to H2Te. As can be seen from the dissociation constant values, the acidic character of the hydrides increases from H2O to H2Te. The increase in acidic character is due to the decrease in the He bond dissociation enthalpy from H2O to H2Te. Except for water, all the other hydrides act as reducing agents. The reducing property of these hydrides increases from H2S to H2Te. This is again due to the decrease in their thermal stability from H2S to H2Te. All the elements of this group react with oxygen to form dioxides and trioxides of the type EO2 and EO3 respectively, where E could be sulfur, selenium, tellurium, or polonium. Both these types of oxides are acidic in nature. Ozone, which is treated as a dioxide of oxygen, and sulfur dioxide are gases, while selenium dioxide and tellurium dioxide are solids. The reducing property of these dioxides decreases from sulfur dioxide to tellurium dioxide. Sulfur dioxide is a reducing agent, whereas tellurium dioxide is a good oxidizing agent. Sulfur trioxide is the only important triode in this group. At room temperature, sulfur trioxide is a solid and exists in three distinct forms: alpha, beta, and gamma. Group 16 elements form a large number of halides of the type EX6, EX4, and EX2, where E is a group 16 element and X is a halogen. Among hexaldehydes, only hexafluorides are stable. They are all colorless gases. they undergo sp3d2 hybridization and hence have octahedral geometry. Sulfur hexafluoride is an extremely inert, colorless, odorless, and non-flammable gas and is insoluble in water. Among the tetrafluorides of group 16 elements, sulfur tetrafluoride is a gas, selenium tetrafluoride is a liquid, and tellurium tetrafluoride a solid. These tetrafluorides undergo sp3d hybridization and hence have trigonal bipyramidal geometry in which one of the equatorial positions is occupied by a lone pair of electrons. This geometry is also known as seesaw geometry. Except for selenium, all the other elements of this group form dichlorides and dibromides. These dihalides are formed by sp3 hybridization and thus have tetrahedral geometry. The presence of a lone pair of electrons gives it a bent geometry similar to that of water. Monohalides exist as E2X2 and are dimeric in nature. Monohalides undergo disproportionation and are converted into tetrahalides. For example, selenium monochloride disproportionation to form selenium tetrachloride and selenium. The structure of these monohalides is similar to that of hydrogen peroxide with a bond angle of 104 degrees. Dioxygen is prepared by different methods in the laboratory and commercially. Let us first study the laboratory methods. The most convenient method for preparing dioxygen in the laboratory involves the catalytic decomposition of solid potassium chlorate. Manganese dioxide is used as the catalyst in this reaction. The other laboratory method is the thermal decomposition of oxides of metals from the lower part of the electrochemical series. For example, the thermal decomposition of silver oxide or mercuric oxide gives dioxygen. Dioxygen may also be obtained in the laboratory by heating the higher oxides of some metals like lead, barium, and manganese. The thermal decomposition of salts rich in oxygen, such as nitrates, for example, potassium nitrate or sodium nitrate, and permanganates, for example, potassium permanganate, also yields dioxygen. Commercially, dioxygen is prepared by either the fractional distillation of liquid air or by the electrolysis of water. To prepare dioxygen from air free from water and carbon dioxide is first liquefied. The remaining constituents of liquid air, primarily liquid oxygen and liquid nitrogen, are separated by means of fractional distillation. The electrolysis of water containing a small amount of sulfuric acid or barium hydroxide leads to the liberation of oxygen at the anode and hydrogen at the cathode. Now, let's discuss the properties of dioxygen. Dioxygen is a colorless, tasteless, and odorless gas. It is slightly heavier than air. It is slightly soluble in water to the extent of 3.08 cubic centimeters in 100 cubic centimeters of water at 293 Kelvin. This small quantity of dissolved dioxygen is just sufficient to support marine and aquatic life. It can be liquefied under pressure to a pale blue liquid by compressing the gas at 90 Kelvin. It can also be solidified into a bluish-white solid at 55 Kelvin. It has 3 isotopes forms with mass numbers 16, 17, and 18. In spite of having an even number of electrons, dioxygen exhibits paramagnetic behavior. This property can be clearly explained by the molecular orbital structure of the dioxygen molecule. Let's now see the chemical properties of dioxygen. Dioxygen is a very reactive element and reacts directly with nearly all metals and non-metals. However, it does not react directly with some metals like gold and platinum, and some noble gases like helium, neon, and argon. In spite of the great reactivity of dioxygen, some external heating is required to initiate the reaction, as the bond dissociation enthalpy of the oxygen-oxygen double bond is very high. However, as the reactions are highly exothermic, once started, they proceed rapidly without further application of heat. Let's see the reaction of dioxygen with metals. Most metals burn in dioxygen and form oxides that are mostly basic in nature. The reactions of dioxygen with metals such as calcium and sodium are shown here. Similarly, most non-metals burn in dioxygen to form acidic oxides. The reactions of dioxygen with sulfur, carbon, and phosphorus are illustrated here. Let's look at the reactions of dioxygen with some compounds. Sulfur dioxide undergoes catalytic oxidation in the presence of vanadium pentoxide to form sulfur trioxide. This is an important step in the manufacture of sulfuric acid by the contact process. Similarly, hydrochloric acid undergoes oxidation in the presence of copper chloride to form chlorine. This reaction forms the basis of Deacon's method for the preparation of chlorine, which is obsolete now. Dioxygen reacts with several organic compounds, such as hydrocarbons and carbohydrates on ignition, forming carbon dioxide and water. Now let's look at the uses of dioxygen. The main importance of dioxygen lies in its support to vital processes, such as combustion and respiration. Dioxygen mixed with carbon dioxide or helium is used for artificial respiration. It is used in the manufacture of many metals. It is used in oxyacetylene welding and metal cutting. It is used to oxidize ammonia in the manufacture of nitric acid. Oxygen cylinders are widely used in hospitals, high-altitude flying, and in mountaineering. Liquid oxygen is an important constituent of the fuel used in rockets. Ozone is an unstable triatomic allotropic form of oxygen. It is present in the atmosphere for about 20 kilometers above sea level. It is formed from the oxygen present there under the influence of ultraviolet light from the sun. Ozone is of vital importance in protecting the Earth's surface from excessive exposure to ultraviolet radiations. However, the use of chlorofluorocarbons in aerosols and refrigerators and their subsequent release into the atmosphere is blamed for making holes in the ozone layer over the Arctic and Antarctic regions. It is feared that this will allow excessive UV light to reach the Earth, which can cause skin cancer in humans. Studies have shown that oxides of nitrogen, particularly nitric oxide, combine rapidly with ozone to form nitrogen dioxide and oxygen. Thus, the oxides of nitrogen released from the exhaust systems of supersonic jet aeroplanes slowly deplete the ozone layer. Let's now look at the preparation of ozone. Ozone is prepared by passing a silent electric discharge through dry, pure and cold oxygen in a special apparatus called the ozonizer. Concentrations of up to 10% of ozone are obtained in this way. The formation of ozone is an endothermic reaction. It must be carried out at high temperature. Hence, it is prepared by means of silent electric discharge. Otherwise, sparking would generate heat and decompose ozone. Higher concentrations or pure ozone can be obtained by fractional liquefaction of an oxygen-ozone mixture. Let's look at the physical properties of ozone. Ozone is a pale blue gas with a characteristic fishy smell. It condenses at -120 degrees centigrade as a dark blue liquid. This, on further cooling, gets solidified to violet-black crystals. Small concentrations of ozone are harmless. However, when the concentration rises above 100 parts per million, breathing becomes uncomfortable and causes headache and nausea. Ozone is thermodynamically unstable and decomposes to oxygen. The decomposition is exothermic and is catalyzed by many materials. Hence, high concentrations of ozone are dangerously explosive. Let's look at the oxidizing action of ozone. Due to the ease with which it liberates atoms of nascent oxygen, ozone acts as a powerful oxidizing agent, second only to fluorine. It reacts much more readily than dioxygen. For example, it oxidizes lead sulfide to lead sulfate, nitrogen dioxide to dinitrogen pentoxide, and iodide ions to iodine. The amount of ozone in a gas mixture may be determined quantitatively by passing the mixture through a potassium iodide solution buffered with a borate buffer. The iodine that is liberated in the reaction is titrated with a standard sodium thiosulfate solution. The amount of iodine consumed in this reaction gives the amount of ozone present in the gas mixture. Let's study the structure of ozone. The ozone molecule is symmetrical and bent with a bond angle of about 117 degrees. The length of the two oxygen-oxygen bonds in the ozone molecule is the same, that is, 128 picometers. This bond length is intermediate between a single bond and a double bond. Ozone is, therefore, considered a resonance hybrid of the canonical forms shown here. Let's look at some important uses of ozone. Ozone is used as a germicide. Ozone is also used as a disinfectant. For example, it is used to purify drinking water, since it destroys bacteria and viruses. Since it decomposes readily to give nascent oxygen, it is used as a mild bleaching agent for bleaching oils, ivory, starch, flour, wax, and delicate fabrics. It is used in the manufacture of potassium permanganate from potassium manganate. It is also used in the manufacture of artificial silk and synthetic camphor. The elements in group 18 are helium, neon, argon, krypton, xenon, and radon. These elements are collectively referred to as noble gases. The term noble gases implies that these elements tend to be chemically inert or unreactive, just as noble metals that show reluctance to react under normal conditions. However, compounds of xenon, such as fluorides, oxides and oxyfluorides, and fluorides of krypton are known. These compounds can be prepared only under drastic conditions at high pressure and temperature. Now let's look at the electronic configuration of the group 18 elements. The general valence shell electronic configuration of these elements is Ns2-Np6, except for helium. Note that the electronic configuration of helium is 1s2. Although helium does not possess an octet, it resembles other elements of the 18th group. The electronic configuration of these elements are listed in the table here. You can see from the table that the Np subshell is completely filled in all the elements. Due to the duplet or octet configuration in their valence shells, the elements of this group are highly stable. In other words, as these elements have closed shell structures, they have less or no tendency to form compounds. As these elements do not have a tendency to lose, gain, or share electrons with atoms of other elements, their valency is 0. The stability or inert nature of these elements is further attributed to the symmetrical arrangement of their electrons. Let's now discuss the occurrence of these elements. Owing to their inert nature, all the noble gases occur in free state. All the noble gases, helium, neon, argon, krypton and xenon, except radon, occur in the atmosphere. Note the percentage abundance of these elements listed here in the table. These gases make up approximately 1% by volume of the atmosphere, in which argon alone constitutes 0.93%. As argon is quite abundant in air, it can be obtained from liquid air by fractional distillation. On the contrary, since helium is scanty in the atmosphere, its recovery from air would become highly expensive. Natural gas deposits are the most important commercial and economical source of helium. Helium is also found in the minerals of radioactive elements, uranium and thorium, such as clevite, monazite, and pitchblende. These minerals give off helium gas on being chemically treated. certain water springs contain helium, neon, and argon in the form of dissolved gases. Radon is a radioactive substance that is produced by the decay of radium and thorium minerals. Let us now discuss the trends in some of the atomic properties of the group 18 elements. The table here lists the trends in some of the atomic properties of the group 18 elements. The atomic radii increase on descending the group with an increase in the atomic number. This is because of the addition of a new shell at each successive element on descending the group. Talking again about their electronic configuration, you know that these elements have closed shell structures, which render them stable. As a consequence, these elements have very high ionization potentials. In other words, the removal of electrons from the valence shell is very difficult. However, you can see from the table that ionization enthalpies decrease gradually on descending the group with an increase in the atomic size. Note that the ionization enthalpy of a noble gas is the highest among the elements of the same period. Again, because the elements of group 18 have stable electronic configurations, they do not have a tendency to accept electrons. Hence, they have very high positive values of electron gain enthalpy. Sulfur has more allotropic forms than any other element. The two common crystalline forms are alpha or rhombic sulfur and beta or monoclinic sulfur. Rhombic sulfur is stable at room temperature, while monoclinic sulfur is stable above 369 Kelvin. These two forms change reversibly with slow heating or slow cooling. Rhombic or alpha sulfur occurs naturally as large yellow crystals in volcanic areas. Crystals of rhombic sulfur are formed by evaporating a solution of rolled sulfur in carbon disulfide. It has a melting point of 385.8 Kelvin and a specific gravity of 2.06. It is insoluble in water, but readily soluble in carbon disulfide. Monoclinic, prismatic or beta sulfur is prepared by melting sulfur in a dish and cooling it till a crust is formed. 2 holes are made in the crust and the remaining liquid is poured out. On removing the crust, colorless needle-shaped crystals of beta sulfur are formed. It is soluble in carbon disulfide. It has a melting point of 393 Kelvin and a specific gravity of 1.98. Monoclinic sulfur is stable above 369 Kelvin. Below this temperature, it turns into alpha sulfur. Alpha sulfur, on the other hand, is stable below 369 Kelvin and turns into beta sulfur above this temperature. At 369 Kelvin, both the forms are stable. The temperature at which the two forms are stable is called transition temperature, and the two varieties are called enantiotropic substances. Both these allotropic forms contain puckered S8 rings with a crown conformation and differ only in the overall packing of the rings in the crystal. In each ring, the atoms lie in two parallel planes, with the angles between the bonds all being 107 degrees and the bond lengths being 204 picometers. Several other rings, S7, S9, S10, S11, S12, S18 and S20 have been synthesized in the last 2 decades. In all of these ring compounds, the SS distance is 204 picometers. In cyclo S6, the ring adopts the chair form. The structure and the molecular dimensions are illustrated in the image here. Sulfur melts to form a mobile liquid. As the temperature is raised, the color darkens. The S8 rings break at 433 Kelvin. Sudden cooling of this liquid in water gives plastic sulfur or gamma sulfur. The vapor at 473 Kelvin consists mostly of S8 rings, but contains 1 to 2% of S2 molecules. At 1000 Kelvin, the gas mainly consists of S2 molecules. Like oxygen, the S2 molecule contains 2 unpaired electrons in the anti-bonding pi star orbitals, and hence exhibits paramagnetism like it. Sulfur forms a large number of oxoacids. Many of these do not exist as free acids, but are known as anions and salts. Oxoacids of sulfur, depending on their structural similarities, are divided into 4 series. They are Sulfuric Acid series, Sulfuric Acid series, Ionic Acid series, Peroxoacid series. Oxoacids with SS linkages are called thioacids, while those with peroxo linkages are called peroxoacids. The table here shows the names, structures, and oxidation states of sulfur in its various oxoacids. As you can see, sulfurous acid, di- or pyrosulfurous acid, and dithionic acid are categorized under the sulfurous acid series. Sulfuric acid, thiosulfuric acid, and di- or pyrosulfuric acid are grouped under the sulfuric acid series. The thionic acid series includes dithionic acid and polythionic acid, while the peroxo acid series includes peroxomonosulfuric acid and peroxodisulfuric acid. Among these oxoacids, sulfuric acid is the most important acid used in the chemical industry. It is manufactured by the contact process. The contact process involves 3 steps. The first step is the production of sulfur dioxide. This can be made by burning sulfur or sulfide ores such as iron pyrites in excess of air. The second step is the formation of sulfur trioxide. Sulfur dioxide is oxidized to sulfur trioxide with atmospheric oxygen in the presence of vanadium pentoxide as catalyst. The third step is the conversion of sulfur trioxide into sulfuric acid. The sulfur trioxide formed in the second step is dissolved in 98% sulfuric acid to give pyrosulfuric acid or oleum. Oleum is then diluted with water to give sulfuric acid of the desired concentration. The plant used for the contact process is shown here. The plant includes pyrites burners or sulfur burners, dust precipitator, washing and cooling tower, drying tower, arsenic purifier, preheater, catalytic converter, and absorption tower. Let's briefly discuss the different stages involved in the manufacture of sulfuric acid by this process. The sulfur or iron pyrites are burned in the sulfur burner to produce sulfur dioxide. The impure sulfur dioxide and oxygen gases from the sulfur burner are passed into the dusting tower where the dust particles are removed by settling down. The purified gases are now passed into the washing and cooling tower. Here, the gases are cooled and washed. The moist gases from this tower are passed into the drying tower. The gases are dried by a spray of concentrated sulfuric acid. The dry gaseous mixture from the tower is then passed through the arsenic purifier. The main impurity in the gases, arsenic oxide, is removed here. The pure gases are passed through a preheater and heated to about 673 to 723 Kelvin. Gases are then led into the catalytic converter. Here, in the presence of vanadium pentoxide as catalyst, sulfur dioxide and oxygen combine to form sulfur trioxide. The sulfur trioxide is then led into the adsorption tower. In the absorption tower, sulfur trioxide is absorbed in concentrated sulfuric acid to form oleum. The oleum is diluted with water to get the acid at the required concentration. The key step in the manufacture of sulfuric acid is the catalytic oxidation of sulfur dioxide to sulfur trioxide with atmospheric oxygen. The forward reaction is exothermic and is favored by a low temperature. Since there is a decrease in the number of moles of gas, the process is favored by a high pressure. Hence, low temperature and high pressure are the favorable conditions for maximum yield. However, the temperature should not be too low, as the reaction would then become slow. In practice, the reaction is carried out at a pressure of 2 atmospheres and a temperature of 720 Kelvin. The sulfuric acid obtained by this process is 96 to 98% pure. Let's now look at the physical properties of sulfuric acid. Sulfuric acid is a colorless, dense, oily liquid with a specific gravity of 1.84 at 298 Kelvin. It has a boiling point of 611 Kelvin. The high boiling point and viscous nature is due to hydrogen bonding, because of which a number of simple molecules bind together to form a cluster. Concentrated sulfuric acid has a strong affinity for water. A large amount of heat is produced when the acid is mixed with water. The temperature may rise to as high as 393 Kelvin. Hence, the acid is always diluted by adding it to water slowly with constant stirring. Remember, never add water to sulfuric acid. The evolution of heat is due to the formation of hydrates such as H2SO4, H2O, H2SO4, 2H2O, and H2SO4, 4H2O. Let's now study the chemical properties of sulfuric acid. The chemical reactions of sulfuric acid are due to its low volatility, strong acidic character, strong affinity for water, and ability to act as an oxidizing agent. Sulfuric acid is a strong dibasic acid. In an aqueous solution, it ionizes in 2 steps, as shown here. Note that the value of dissociation constant, Ka1, for the first step is very large as compared to the second step. The larger value of Ka1 indicates the greater extent of ionization of H2SO4 into H+ and HSO4-, which in turn indicates the greater acidic strength of the acid. The acid neutralizes alkalis and forms 2 series of salts, bisulfates and sulfates. For example, concentrated sulfuric acid reacts with sodium hydroxide and forms sodium bisulfate and sodium sulfate, as shown in the equations here. Sulfuric acid, being less volatile, is used in the manufacture of more volatile acids from their corresponding salts. For example, concentrated sulfuric acid liberates hydrogen fluoride from calcium fluoride, and hydrogen chloride from sodium chloride. Concentrated sulfuric acid is a powerful dehydrating agent. The dehydrating property is used in drying many wet gases that do not react with the acid. For example, gases like chlorine, sulfur dioxide, and hydrochloric acid are dried by passing them through sulfuric acid. Sulfuric acid also removes water from organic compounds like carbohydrates. For example, it chars sugarcane, glucose, and starch to carbon. Hot concentrated sulfuric acid is a good oxidizing agent. It oxidizes both metals and non-metals and itself gets reduced to sulfur dioxide. For example, hot concentrated sulfuric acid oxidizes copper to copper sulfate and gets reduced to sulfur dioxide. Similarly, it oxidizes non-metallic carbon to carbon dioxide and itself gets reduced to sulfur dioxide. Lastly, let's look at the important uses of sulfuric acid. Sulfuric acid, because of its wide applications, is referred as the king of chemicals. It is used in the manufacture of fertilizers like ammonium sulfate and superphosphate, dyes, pigments, and paints. Explosives such as TNT. Other important chemicals like hydrochloric acid, nitric acid, phosphoric acid, and sodium carbonate. It is used in the refining of petroleum. Sulfuric acid is also used as a pickling agent. Pickling is an industrial process for removing layers of basic oxides from metals like iron and copper before electroplating, enameling, soldering, and galvanizing. As a laboratory agent and a dehydrating and oxidizing agent. Sulfur forms a large number of oxoacids. Many of these do not exist as free acids, but are known as anions and salts. Oxoacids of sulfur, depending on their structural similarities, are divided into 4 series. They are sulfurous acid series, sulfuric acid series, thionic acid series, peroxoacid series. Oxoacids with SS linkages are called thioacids, while those with peroxo linkages are called peroxoacids. The table here shows the names, structures, and oxidation states of sulfur in its various oxoacids. As you can see, sulfurous acid, di- or pyrosulfurous acid, and dithionic acid are categorized under the sulfurous acid series. Sulfuric acid, thiosulfuric acid, and di- or pyrosulfuric acid are grouped under the sulfuric acid series. The thionic acid series includes dithionic acid and polythionic acid, while the peroxo acid series includes peroxomonosulfuric acid and peroxodisulfuric acid. Among these oxoacids, sulfuric acid is the most important acid used in the chemical industry. It is manufactured by the contact process. The contact process involves 3 steps. The first step is the production of sulfur dioxide. This can be made by burning sulfur or sulfide ores such as iron pyrites in excess of air. The second step is the formation of sulfur trioxide. Sulfur dioxide is oxidized to sulfur trioxide with atmospheric oxygen in the presence of vanadium pentoxide as catalyst. The third step is the conversion of sulfur trioxide into sulfuric acid. The sulfur trioxide formed in the second step is dissolved in 98% sulfuric acid to give pyrosulfuric acid or oleum. Oleum is then diluted with water to give sulfuric acid of the desired concentration. The plant used for the contact process is shown here. The plant includes pyrites burners or sulfur burners, dust precipitator, washing and cooling tar, drying tar, arsenic purifier, preheater, catalytic converter, and absorption tar. Let's briefly discuss the different stages involved in the manufacture of sulfuric acid by this process. The sulfur or iron pyrites are burned in the sulfur burner to produce sulfur dioxide. The impure sulfur dioxide and oxygen gases from the sulfur burner are passed into the dusting tar, where the dust particles are removed by settling down. The purified gases are now passed into the washing and cooling tar. Here, the gases are cooled and washed. The moist gases from this tar are passed into the drying tar. The gases are dried by a spray of concentrated sulfuric acid. The dry gaseous mixture from the tar is then passed through the arsenic purifier. The main impurity in the gases, arsenic oxide, is removed here. The pure gases are passed through a preheater and heated to about 673 to 723 Kelvin. Gases are then led into the catalytic converter. Here, in the presence of vanadium pentoxide as catalyst, sulfur dioxide and oxygen combine to form sulfur trioxide. The sulfur trioxide is then led into the adsorption tar. In the absorption tar, sulfur trioxide is absorbed in concentrated sulfuric acid to form oleum. The oleum is diluted with water to get the acid at the required concentration. The key step in the manufacture of sulfuric acid is the catalytic oxidation of sulfur dioxide to sulfur trioxide with atmospheric oxygen. The forward reaction is exothermic and is favored by a low temperature. Since there is a decrease in the number of moles of gas, the process is favored by a high pressure. Hence, low temperature and high pressure are the favorable conditions for maximum yield. However, the temperature should not be too low, as the reaction would then become slow. In practice, the reaction is carried out at a pressure of 2 atmospheres and a temperature of 720 Kelvin. The sulfuric acid obtained by this process is 96 to 98% pure. Let's now look at the physical properties of sulfuric acid. Sulfuric acid is a colorless, dense, oily liquid with a specific gravity of 1.84 at 298 Kelvin. It has a boiling point of 611 Kelvin. The high boiling point and viscous nature is due to hydrogen bonding, because of which a number of simple molecules bind together to form a cluster. Concentrated sulfuric acid has a strong affinity for water. A large amount of heat is produced when the acid is mixed with water. The temperature may rise to as high as 393 Kelvin. Hence, the acid is always diluted by adding it to water slowly with constant stirring. Remember, never add water to sulfuric acid. The evolution of heat is due to the formation of hydrates such as H2SO4, H2O, H2SO4, 2H2O, and H2SO4, 4H2O. Let's now study the chemical properties of sulfuric acid. The chemical reactions of sulfuric acid are due to its low volatility, strong acidic character, strong affinity for water, and ability to act as an oxidizing agent. Sulfuric acid is a strong dibasic acid. In an aqueous solution, it ionizes in 2 steps, as shown here. Note that the value of dissociation constant, Ka1, for the first step is very large as compared to the second step. The larger value of Ka1 indicates the greater extent of ionization of H2SO4 into H+ and HSO4-, which in turn indicates the greater acidic strength of the acid. The acid neutralizes alkalis and forms 2 series of salts, bisulfates and sulfates. For example, concentrated sulfuric acid reacts with sodium hydroxide and forms sodium bisulfate and sodium sulfate, as shown in the equations here. Sulfuric acid, being less volatile, is used in the manufacture of more volatile acids from their corresponding salts. For example, concentrated sulfuric acid liberates hydrogen fluoride from calcium fluoride. and hydrogen chloride from sodium chloride. Concentrated sulfuric acid is a powerful dehydrating agent. The dehydrating property is used in drying many wet gases that do not react with the acid. For example, gases like chlorine, sulfur dioxide, and hydrochloric acid are dried by passing them through sulfuric acid. Sulfuric acid also removes water from organic compounds like carbohydrates. For example, it chars sugarcane, glucose, and starch to carbon. Hot concentrated sulfuric acid is a good oxidizing agent. It oxidizes both metals and non-metals and itself gets reduced to sulfur dioxide. For example, hot concentrated sulfuric acid oxidizes copper to copper sulfate and gets reduced to sulfur dioxide. Similarly, it oxidizes non-metallic carbon to carbon dioxide and itself gets reduced to sulfur dioxide. Lastly, let's look at the important uses of sulfuric acid. Sulfuric acid, because of its wide applications, is referred as the king of chemicals. It is used in the manufacture of fertilizers like ammonium sulfate and superphosphate, dyes, pigments, and paints. Explosives such as TNT. Other important chemicals like hydrochloric acid, nitric acid, phosphoric acid, and sodium carbonate. It is used in the refining of petroleum. Sulfuric acid is also used as a pickling agent. Pickling is an industrial process for removing layers of basic oxides from metals like iron and copper before electroplating, enameling, soldering, and galvanizing. As a laboratory agent and a dehydrating and oxidizing agent. The elements in group 17 are fluorine, chlorine, bromine, iodine, and astatine. These elements are collectively referred to as the halogens. The term halogens is derived from the Greek words halo, which means salt, and gens, which means born. That is, the word halogens means salt-producing in Greek. In other words, these elements react with metals to form salts. Now let's look at the electronic configuration of the group 17 elements. The valence shell electronic configuration of these elements is ns2np5. So, it is evident that these elements have 7 electrons in their valence shells. The electronic configurations of these elements are listed in the table here. You can see from the table that the valence shell is short of an octet by 1 electron. As these elements need 1 electron to attain stable octet or nearest inert gas configuration, they have a strong tendency to either gain 1 electron to form an ionic bond, or share an electron with another atom to form a covalent bond. The halogens constitute the most reactive group of nonmetals. The high reactivity of the halogens is attributed to their strong tendency to acquire or share an electron to attain the nearest inert gas configuration. Let's now discuss the occurrence of these elements. Owing to their high reactivity, the halogens do not occur in free state, but in combined state in nature, except for astatine. Note that astatine is radioactive and has a short half-life. The table here lists the abundance of these elements in the Earth's crust by weight. You can see from the table that fluorine and chlorine are relatively more abundant than others. Note that fluorine is the 13th and chlorine the 20th most abundant element by weight in the Earth's crust. Fluorine occurs widely as insoluble fluorides, such as fluorspar, cryolite, and fluorapatite. Of these, the main source is fluorspar. Small amounts of fluorine are present in soil, plants of river water, and the bones and teeth of animals. Chlorine, bromine, and iodine are present in seawater in the form of chlorides, bromides, and iodides of highly active metals like sodium, potassium, magnesium, and calcium. Of these, the most abundant is sodium chloride. Seawater consists about 1.5% by weight of sodium chloride. The dry beds of seas also contain large deposits of sodium chloride along with smaller proportions of calcium chloride and carnallite. Iodides are found in traces in seawater. The principal source of iodine is seaweeds and crude chili salt petre. The percentage abundance of iodides in these compounds is given here. The atomic properties of group 17 elements are given in the table here. Let us begin our discussion with the trends in atomic and ionic radii. A comparison of these two tables shows that as we move down the group, the atomic radii and ionic radii increase due to the addition of a new principal energy level in each successive element. However, these elements have the least atomic radii when compared to other elements in the corresponding periods. This is because of maximum effective nuclear charge. Now let's look at ionization enthalpy. Group 17 elements show very high values of ionization enthalpy. As a consequence, the atoms of these elements have little tendency to lose electrons and form positive ions. However, as we move down the group, the value of ionization energy decreases. This is due to the gradual increase in the atomic size, which reduces the force of attraction between the valence electrons and the nucleus. You can see from the table that the ionization enthalpy of fluorine is appreciably higher than any other halogen, which is attributed to its small size. Halogens have the maximum negative electron gain enthalpy in the respective periods. This stems from the fact that in the atoms of these elements, the valence shell is short of an octet by only one electron. Moreover, these elements have the maximum effective nuclear charge and the smallest atomic radii in their respective periods. Hence, these elements have a strong tendency to accept an electron and attain nearest noble gas configuration. The electron gain enthalpy becomes less negative on descending the group. However, fluorine has less negative electron gain enthalpy than chlorine. That is, chlorine has the maximum negative electron gain enthalpy among all the elements. It is because of the small size and compact 2p subshell of the fluorine atom. Owing to the small size of the fluorine atom, the incoming electron experiences a greater amount of repulsion from the electrons that are already present. In other words, the electron-electron repulsions between the incoming electron and the electrons already present outweigh the attraction between the added electron and the nucleus. The halogens have very high electronegativity values. You can see from the values of electronegativity in the table that the electronegativity decreases gradually on moving down the group from fluorine to iodine due to the corresponding increase in the atomic radii. Note that fluorine is the most electronegative element in the periodic table.